In this video, we're going to talk about implicit differentiation. We're kind of expanding on the idea of the chain rule, and specifically we are going to look at this portion or this notation of the chain rule where we're saying the derivative of y with respect to x equals the derivative of y with respect to some function u, which we have noted above as g of x, times the derivative of that u with respect to x. So this again is just the chain rule, and we're going to see some similarities to what we've been doing. We're going to see some differences with what we've been doing. Let's start with an example that we know and love. Y equals x cubed. Now this one you probably already know what the derivative of this is, but we haven't used in the past the dy over dx notation. So what we're going to do is we're going to take the derivative of y with respect to x, and we're going to set that equal to the derivative of x cubed with respect to x. Alright, so the derivative of y with respect to x, that's our y prime like we normally would write. But the derivative of x cubed with respect to x, well, these two things are the same. The two variables are the same. The x's are the same, I should say. So that's what we're differentiating, right? That's what we're used to manipulating. So we know that that's going to be 3x squared. But what happens if we have y squared equals x? Alright, now if we were to find the derivative of this, well, we can't because we've got y squared. So what we want to do is we're going to want to take the square root of both sides, get y by itself, and we know that's going to be plus or minus the square root of x. Now, this first function, y squared equals x, sorry, it's not a function, it's an equation. This first equation, y squared equals x, is an implicit function, or equation. I keep on saying function. It's an implicit equation because this thing is squared. The y is squared. What that's saying, it's implying that we could find what y is by taking the square root of x, but it doesn't explicitly state what our function is. And this this equation is. This bottom line is the explicit notation of this equation. The top is the implicit. So we basically want to figure out how to find y, or the derivative of y. So we're going to look at this implicitly, using the implicit notation, and then we'll see how it kind of ties back to our explicit notation that we're used to working with. Okay, so we're going to use our dy, or the dy over du times du over dx, and we're going to use that notation. So we've got y squared equals x. So what we're going to do is we're going to take the derivative of y squared with respect to x, and we're going to set that equal to the derivative of x with respect to x. Okay? So the derivative of let's see, y equals x cubed. All right, let's go back over to here to the left and kind of see how this plays out and use the same notation. So again, if we're taking the derivative of y with respect to x and the derivative of x cubed with respect to x, we know that the derivative of y with respect to x stays the same. Nothing happens there because we can't differentiate it because we've got different variables. We've got a y and an x. We can't do that. So what we're left with is 3x squared. Okay, so over here on the right, we've got 1, which we know the derivative of x with respect to x is 1. Now on the left side, now we're going to start using our chain rule. We're saying that y, we've got y and u up here. So we need to we're going to look at this portion of our chain rule. We're going to use dy over du times du over dx. All right. So let's switch this around a little bit. We're going to say u equals y squared. All right. So that's kind of our embedded function, or our composite function. So du over dx. All right. So I'm switching them around from what I had up in the top in the blue box. So du over dx is going to be equal to du over dy times dy over dx. You notice all I did was switch the y, but you've got the y in the numerator, then the u in the denominator, u in the numerator, x in the denominator. And I just switched them around so you can kind of see how the pattern still follows. So when we use this idea, we're going to say the derivative of u, which is y squared, with respect to y. Okay, so that we can find. So we're gonna find the derivative of y with the derivative of u with respect to y. That's 2y. Okay, so we're just basically finding the derivative of y. Then we're going to be multiplying by the derivative of y with respect to x. Well, we don't have anything for that yet because we're just talking about u and y. We don't have y and x on this side. So we just have 2y times dy of dx. And now if we want to get dy of dx, which is ultimately our goal, we need to divide both sides by 2y. And we're left with dy over dx equals 1 over 2y. Now, I know that this looks a little different than what we've been doing, but let's compare it to our explicit function that we're used to doing. All right? So we said that y is going to equal to plus or minus square root of x. So let's look at these two different pieces, because you could have y equaling the positive square root of x, you could have y equaling the negative square root of x. So y equals the positive square root of x, or x to the 1/2. So we want to take the derivative of this. We're going to have y prime equal 1/2 times, or 1/2 x to the negative 1/2 power. We can put that x in the denominator and convert it to a square root, and we've got 1 over 2 times x, the square root of x, right? But remember that that the square root of x equals y. Those are the same things. So we know that y prime is going to be 1 over 2y. Alright, so let's try this with the other piece. Alright, so we've got y equals negative x to the 1/2 power. Right? Square root of x, make it to an exponent. So we take the derivative of this. Y prime equals negative 1 over 2 square root of x. Well, we can rearrange this by saying this is going to be, put our negative in the denominator and actually move that negative over to our square root. So we've got 1 over 2 times the negative square root of x. Well, we also said y could equal the negative square root of x, so y prime is going to equal 1 over 2y. So here what we've done is we're taking an equation where y is not by itself. It might be squared, it might be cubed, it might have other pieces attached to it, and we're going to use the chain rule to still find the derivative of this function. And what we're going to do is we're going to kind of work it through the entire function. We're going to start thinking of derivatives as an operator, which means kind of like if you square both sides of an equation, or if you add something to both sides of the equation. We're going to take the derivative of both sides of the equation, and we're going to be able to find the derivative of equations where y is not a singular exponent, where it's not by itself. And this will really expand on a lot of the different types of equations that we can look at. So in the next video we'll look at a couple examples, and hopefully this will help get this idea across a little bit further.